So we are live on YouTube, and the recording is on the cloud, in the cloud. So you can get started. Welcome to the Silicon Valley chapter of IEEE Computer Society. I am the chapter chair, Vishnu Pendiala. Ours is the largest chapter in Silicon Valley section of IEEE with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. The section itself is either the largest in the world or one of the largest in the world. So we are uniquely positioned by the virtue of our location and available expertise. And thanks to the online meetings these days, we have access to excellent speakers from all over the world. Like today, today's speaker, Dr. Ashwini Kumar Cherukuri, is a professor at Vellore Institute of Technology, India. He is actually speaking from India. It is, I think, 9:30 his time. His research interests include information security and machine learning. Dr. Ashwini Kumar earned the Young Scientist Fellowship from Tamil Nadu State Council for Science and Technology and was awarded the Inspiring Teacher Award from the Indian Express. Indian Express, some of you may know that it's one of the leading English daily newspapers in India. Dr. Ashwini worked on various research projects funded by the Government of India's Department of Science and Technology, the Department of Atomic Energy, and the Ministry of Human Resource Development. Dr. Ashwini Kumar has published more than 170 refereed research articles in various national and international journals and conferences, and is an editorial board member for several international journals. He is a senior member and distinguished speaker of the Association of Computing Machinery, a member of the IEEE, and vice chair of the IEEE Task Force on Educational Data Mining. He is a distinguished speaker of ACM. He served as the Dean, School of Information Technology and Engineering, VIT, Vellore. And today's topic is security in quantum computing era. We all know the amount of data that is being generated, stored, communicated, and analyzed is increasing at an exponential rate. So securing this data while in storage or in communication, or for that matter in the analysis, is quite challenging. Emerging technologies make this task much more challenging. So quantum computing is such an emerging technology, having large-scale computing capabilities and has the potential to solve some of the problems that conventional computing principle cannot solve. With such potential, it can adversely disrupt the current security frameworks and at the same time address some of the pressing problems in security. So in this talk, Dr. Ashwini introduces threats and challenges in security due to quantum computing. He will address security challenges with quantum principles and developments in post-quantum cryptography as well. Over to you, Dr. Ashwini.
Thank you, Dr. Vishnu. Am I audible, right?
Yes.
So at the outset, I would like to thank Dr. Vishnu for inviting me to this August forum. It's my pleasure and privilege to deliver this talk under the umbrella of IEEE Computer Society chapter of Silicon Valley. So I sincerely thank Dr. Vishnu for giving me this opportunity. So my today talk would be on security, especially information security in the current era of quantum computing. So my talk is structured in the following points. So I'll be providing a brief prologue of the talk. Then I'll be introducing very briefly about the various cryptography algorithms that currently we are using in terms of symmetric encryption techniques. Then we have asymmetric encryption techniques, also the hash functions and the applications of them in the digital signatures. So these are the current cryptography algorithms and techniques what we have that are providing security to our information. Now, then followed by, I'll be briefly touching about the quantum computing principles, especially the various quantum phenomena that quantum computing is based upon. Subsequently, I'll be talking about the quantum algorithms, Shor algorithm as well as the Grover algorithm. Of course, I will be covering more aspects of Shor algorithm. Then I'll be touching about the Grover. Then post-quantum cryptography algorithms that what we have, that also I'll be discussing. Especially we have hash-based cryptography, code-based cryptography. Then we have lattice-based cryptography. But in that, I'll be touching about hash-based cryptography, which is the one of the famous techniques for post-quantum cryptography standards. Then also how quantum principles can be utilized for addressing one of the cryptography challenge, that is that key distribution problem. How quantum principles can be utilized. That also I'll be talking about, especially using the BB84 protocol. Then this would be the points that I will be covering in the current talk. So maybe I will, turn off my video for the, the better utilization of my bandwidth. And so in a current digital world, cryptography is mainly utilized for providing various security objectives. Number one, that is confidentiality, integrity, availability, authentication, non-repudiation. There are various security objectives that are to be met under the current cryptography principles. So no, these principles provide an assurance that information is trustworthy and it is confidential, it is having integrity, it is also authenticated information. So confidentiality is provided especially through the form of encryption of data, and for that purpose we have several schemes. Similarly, integrity is ensured in the form of hash functions and digital signatures. Authenticity is provided by using secret keys. So these are all the various cryptographic principles that are used for ensuring confidentiality, integrity, and authentication, and etc. So cryptography is very essential, and which is the backbone for providing security in any business functionality that we have in the industry. And also the current internet and all our web-based applications are secure because of the cryptography that what we have. So point is, the secured information is typically classified based upon the value of that information. Say, take an example. We have a particular, say, question paper of a examination. The question paper is supposed to be secured till, especially for the before till the exam is conducted. Similarly, so take an example, if a kind of insurance data, the lifetime of such data is maybe about 40 years, 50 years, 60 years. So that means during that duration of data, that particular lifetime of data, the security has to be ensured for such type of data item. So it is all dependent upon type of data, application of such data. All the algorithms that what we are using for cryptography, they are all based upon the classical conventional computing models, which are mathematically strong to support whatever is the lifetime of the data. But the current generation, especially when we are going ahead with the quantum computer, the current cryptography standards are entering into a dangerous zone. Especially in 1994, Peter Shor has introduced a famous algorithm called Shor algorithm, wherein which quantum computers are posing a threat to the current cryptographic standards and techniques. The point is, when this particular algorithm, Shor algorithm, was introduced or envisioned, we don't have technology that materializes a quantum computer. But thanks to the recent developments, wherein which there are steps towards realizing the quantum computer, of course, we have a long way to go to bring a commercial aspect of commercial angle of a quantum computer. But the point is that at least to a few bits, we call it as a qubits, but to some extent, for a few qubits, the quantum computers are there. So that is providing a major processing breakthrough and providing the disruption and bringing the quantum computers, realizing the quantum computers. So if we see the the timeline of the quantum computers, of course, this was introduced or coined the quantum mechanics. The basics of the quantum computers are rooted to the quantum mechanics, which were there from early 1920s. But the point is, with the introduction of Shor algorithm in 1990s, early 1990s, the theory of Shor algorithm has brought the quantum revolution. So till that particular time, all were in the first quantum revolution. But then once the Shor algorithm was proposed, it has entered into the second revolution. So the current at present, there are companies which are trying to achieve quantum supremacy by demonstrating their ability of processing over the certain number of qubits. It is expected that down the line of next 10 to 15 years, we may have a real quantum computer that gets built. And then in such case, as I have mentioned, if the Shor algorithm is implemented over that, all the cryptographic technique, especially the public key based cryptographic techniques, they would be in danger. And hence, what people are viewing is that the attackers may enter into the zone called harvest now, decrypt later, in the sense they may take all the ciphertext that is available at present, and once these quantum computers are realized in the next 10 years zone, and they will be able to break all the public key, break the public key techniques. In such case, with the help of quantum computers, then all our data that is to be secured will be available to the attackers. So that is one of the major concern for the security scientist. So in that regard, under this particular backdrop, this talk explores various cryptographic techniques, which includes symmetric, asymmetric, and digital signature. And this talk also provides a quick summary of quantum computing principles, including the algorithms such as Shor algorithm and Grover algorithm. Subsequently, I'll be talking about post-quantum cryptographic techniques, especially with a focus on hash-based cryptography. Subsequently, I'll be talking about quantum key distribution. This would be my outline of the talk. Look at the cryptography evolution, starting from classical cryptography of the old age to the current generations of modern cryptography. So especially these are all modern cryptography started after late 1940s with the principles to secure the digital world. So the modern cryptography algorithms basically are divided into two approaches. One is called symmetric cryptosystems, and the other one is asymmetric cryptosystems, wherein which we have symmetric cryptosystems. The sender actually tries to take the plain text, encrypt the data with the help of a key, and the receiver, after receiving the ciphertext, which is the encrypted form of the plain text, the receiver would decrypt it with the same key at the receiver side. Since the same key is used at both ends of encryption and decryption, it is called symmetric cryptosystem. The challenge of such cryptosystems is the sharing of the key K at both ends. So how to share the common key between both ends is the major challenge in the symmetric cryptosystems. In order to address this challenge, there are other approaches coming from the mathematical principles called asymmetric cryptosystems, wherein which the sender actually encrypts the plain text, the message that he wants to send, with the help of an encryption key called KE, and the receiver would decrypt that the ciphertext what the receiver has received with the help of a different key called KD. If we look at this, KE is not equal to KD. So, and since it is the two keys are used, one for encryption purpose and another for decryption purpose, it is called asymmetric crypto system. And in this particular scenario, the point is every user, that means the sender and receiver, should have their own key pair. That means if I say the sender should have a public key, sender also should have the private key. Similarly, the receiver will have the public key and the receiver will also have a private key. So the sender will use the receiver's public key for encryption purpose and sends it to the receiver. Receiver decrypts it with the help of the receiver's private key. And obviously, since it is a private key, obviously only the receiver would know that particular private key and no one else knows it. And with that philosophy, we are going to provide confidentiality to the data by encrypting with the help of senders, by encrypting with the help of receiver's public key, we are able to achieve confidentiality. There is another scheme wherein which the sender actually encrypts the data with the help of private key of sender. So when the data is encrypted with the help of private key of the sender, receiver decrypts it with the help of public key of sender. Because it's decryption is happening with the public key, the public key of sender. Since it's a public key, everybody knows. So receiver also knows it. So with this particular scheme, wherein which encryption is happened with the help of private key of sender, the decryption has happened with the help of public key of the sender. This provides the first one provides the confidentiality, the second one provides the authentication. Okay, it ensures that to the receiver that yes, only this particular sender has sent this message, no one else has sent, because the receiver is able to decrypt it with the help of public key of sender. So we are achieving confidentiality, we are achieving authentication based upon the key which we are using for encryption and decryption purpose. So these are the fundamental aspects of symmetric crypto systems and asymmetric crypto systems we have. If you look at the symmetric crypto systems, we have the data encryption standard, one of the first commercial the symmetric scheme we have. This was popular till early 90s, wherein which the plain text, which is of larger size, is divided into 64-bit plain text, and those 64-bit plain text blocks are encrypted with the help of a 64-bit key. And this is the whole process of the data encryption standard, which of course I'm not going to discuss, but the point is that, so this is one of the first versions of symmetric crypto systems that were implemented in the very beginning of digital era. Subsequently, we have advanced encryption standard, wherein which the current symmetric crypto systems are in place. Using the advanced encryption standard, wherein which we take the blocks of plain text and perform certain operations, or we call them as transformations over the blocks of plain text using the key, and that produces the ciphertext. So the advanced encryption standard is one of the most popular, successful, and even current many applications are using this particular standard. And the beauty of that is it actually uses 4 different types of transformations within the cipher generation. But among them, one of the transformation is a nonlinear aspect, and because of that, the advanced encryption standard is proved to be robust and in providing security to the current applications. And another beauty of this particular algorithm is that we can vary the number of keys. Unlike the DES, where the key size is fixed of 64-bit, the advanced encryption standard, we can have a variable length key. So that is the beauty of advanced encryption standard. Coming to the asymmetric crypto systems, the asymmetric crypto systems are also called as public key crypto systems. The reason is that we are, as I've mentioned a few slides back, that we are using public key of the receiver is used for encryption purpose, and hence it is also called as public key cryptography, asymmetric cryptography, and etc. So these particular algorithms are having a lot of applications in the current scenario. So the point is, if we look at the sender is sending the message to the destination, we can achieve both confidentiality as well as authentication by encrypting 2 times. So if we see here, we have taken the message. The encryption algorithm has initially used the private key of sender for encryption purpose. So once we get this is called intermediate ciphertext. So this intermediate ciphertext is again encrypted with the help of public key of receiver. So all this is happening at sender side. So sender knows his private key and hence able to encrypt the plain text, produce the intermediate ciphertext, which is again got encrypted with the help of public key of the receiver. And remember, since it is the public key of the receiver, the public key of the receiver, sender knows it, since it's a public key. So this is the ciphertext. Now this ciphertext is received at the receiving side. Now the receiver is going to decrypt it first with the help of private key. This is with the private key of receiver. So the ciphertext would get decrypted. And remember, this is the private key of receiver, and this is happening at the receiver side. So receiver knows his private key. And once he decrypts, he gets the intermediate ciphertext, that Y here. Then subsequently, Y would get decrypted with the help of the public key of sender. So this is with the public key of sender. So since it's a public key, the receiver knows what is the public key of sender and hence gets the message. So in that aspect, number 1, we are achieving confidentiality. Number 2, we are achieving authentication. Both we are achieving it. So these are the current schemes of public key cryptography. Now, if we look at these aspects, what are all the various algorithms we have? We have RSA algorithm, we have Diffie-Hellman algorithm, we have elliptic curve public key encryption algorithm. So these algorithms are basically used for encryption purpose, for creation of the digital signature purpose, for performing the key exchange. When I say key exchange, this is exchange of symmetric keys. Okay, so if we remember in the beginning, we mentioned that one of the major challenge of the symmetric key algorithms is that how to exchange the common key. So public key algorithms are used for the purpose of exchange of symmetric keys. So this is one of the potential applications. So these are all the various algorithms we have. So let us look at the RSA algorithm, because the RSA algorithm is the one which is to be broken with the help of quantum computer. It was the popular algorithm proposed by Rivest, Sharma, and Edelman in late 1970s. Especially, it uses large integers, which is of 1024-bit length, etc. It is basically a block cipher like AES and DES, which encrypt and decrypt the plain text in the form of blocks. So multiple blocks gets encrypted and then gets decrypted. The beauty of this algorithm is that it is providing security because it is rooted to a fundamental mathematical problem of that is called difficulty to factor the large prime numbers. So this is the fundamental problem that is providing security to the RSA algorithm. Now this problem, if quantum computers are realized, this particular problem would be broken. If it is broken, then security of RSA algorithm would be at fixed. So if you look at the RSA algorithm, what typically we do is we take two distinct large random prime numbers called P and Q, and we calculate their product. Then subsequently we calculate the Euler-Stochant value of the product of these prime numbers, wherein which the Euler-Stochant value of this product can be calculated psi of P into psi of Q, and subsequently what we do is we select a random integer E such that that random integer is less than the tangent value, and further it is relatively prime to psi of n. That means the GCD value of E and psi of n is 1. Further, we compute a unique integer D such that the E and D are multiplicative inverses at mod psi of n. Further, D should be relatively prime to n. Now what happens? Among these values, the public key is n comma E and the private key is declared as D. So this is how we generate the key pairs of every node in the network or the communicating parties like sender and receiver. So now further we perform encryption. Suppose the plain text is M, the plain text would be converted into ciphertext by performing C is equal to M power E mod n, and the decryption is take the ciphertext. Since D is the private key, so the decryption happens M is equal to C power D mod n. So this is a simple algorithm of RSA. It looks simple, but the point is that it has inherent complexity in terms of generating the large prime numbers and calculating the subsequent variables of this algorithm. The beauty of this algorithm is that it is rooted to we are able to find the product of the so if you look at the algorithm, we are able to find the product of these values, but subsequently if we want to calculate the D value, we need the psi of n. That means for that purpose we need the prime factors, which we don't have the algorithm that is able to produce that. Of course, there are certain algorithms, but when having large values, say 1024-bit or 2048-bit, for the large keys, we don't have an efficient algorithm that can solve this particular problem. So this particular problem is the one which is providing security to the RSA algorithm. Subsequently, we have Diffie-Hellman algorithm, which is another public key algorithm. This is also a popular algorithm. The purpose of this algorithm is to exchange the key. When I say exchange key, so the key what we are going to exchange would be the symmetric key. Once the key is exchanged, that algorithm we can apply is the symmetric algorithm. So the Diffie-Hellman algorithm, if we look at both communicating parties like Alice and Bob, they know a common numbers called P and Q, where PQ are the prime numbers, and they also know they know two publicly known numbers P and as well as its primitive root A. Once Alice and Bob knows these values P and A, the prime number and its primitive root, the Alice calculates a random integer called XA in the form of the primitive root power XA mod P. So this XA is the secret to Alice. In the same manner, Bob also selects a random integer called XB and calculates YB. How YB is calculated? A power XB mod P. Now XB is private to Bob. Similarly, XA is private to Alice. YA is public key of Alice and Bob knows this. YB is public key of Bob and Alice knows this. So exchange of YA and YB values happens. Once these values are exchanged, Alice calculates the key in the form of YB power XA mod P. Similarly, Bob calculates the key in the form of YA power XB mod P. So YA is the Alice key and XB is the Bob secret key. So Bob calculates the key. Similarly, the Alice also calculates, and it happens that both values are same, and hence the key gets exchanged. So the point is that in the case of an attacker C, the attacker knows the prime number, primitive root, and the public values of Alice and Bob. In order to derive the secret value of either Bob or Alice, what actually attacker has to solve is attacker has to calculate the discrete logarithm to determine the secret value. So it is in the case of calculating discrete in this scenario, it is relatively easy to calculate the exponential modulus prime, but it is very difficult to calculate the discrete logarithms. So this is another fundamental problem wherein which the Diffie-Hellman, which is the popular asymmetric algorithm, is based upon, or the strength of the Diffie-Hellman algorithm that lies. We don't have the solutions or techniques that can address this problem on a classical computer. This is providing strength to the public key cryptography algorithms. Another important dimension of the cryptography is the key management and distribution. As I have already mentioned, how do I share the symmetric key between communicating parties? So there are various schemes, but the point is that at present, what actually we are doing is we are using asymmetric encryption techniques for exchange of the symmetric keys. Similarly, when it comes to the public keys, the distribution of public keys is becoming a major problem in the sense that how do the other node or other communicating parties knows for in an authenticated manner what is the public key of other node, so that no attacks are possible in this scenario. So for that particular purpose, we have the digital certificates and also the public key infrastructure. These are the aspects that are there in the key management. Of course, we are discussing about this. The beauty is that with the help of quantum computing principles, we can address the key management and distribution aspect. Now, we have another category of cryptography algorithms called hash functions, which is the purpose to ensure the integrity of the algorithms, integrity of the message. So we take the message, apply a hash function that produces a digest. At the receiver side, the receiver would receive the message, calculate the hash. If the hash is same as the received hash, then message is retained. Otherwise, message is discarded. Okay. So the hash function's purpose is to ensure that or verify that the integrity of the message is prevailing or not. And for that particular purpose, we have algorithms called Shor 512, message digest, Shor 256. But the current standard is to use Shor 512. The reason for showing this is we are going to have hash-based cryptography as a post-quantum cryptography algorithms. So for that purpose, this is the backbone. On top of the hash algorithms, we have message authentication codes, wherein which the message from the sender would be hashed by the help of a key. So we are going to create a message authentication code. So typically, standard hash algorithms are called keyless ciphers, but message authentication codes are also called keyed hash algorithms. Okay, so the reason is that along with the message, we are also supplying a key and producing a message authentication code. So message and the message authentication code are communicated to the receiver through an insecure communication channel. Upon receiving the message and message authentication code, what the receiver would do is he takes the message and applies the key, same key, and calculates the hash, and that produces the message authentication code. So if the message authentication code that is received and the calculated message authentication code both are same, then we accept the message, otherwise we discard the message. So this is used to verify authentication of the message and also to ensure integrity of the message. Remember, since the message is sent as it is, there is no confidentiality. So our objective is to not provide confidentiality, but just to provide integrity of ensure the integrity of the message. So for that purpose, we have message authentication codes. On top of message authentication codes, we have digital signatures, wherein which the purpose of message authentication protects the two parties who exchange the message from any third party. So that means if we look at in the scenario, in this insecure channel, we are verifying that no attacker is compromising or modifying the contents of the message. So for that particular purpose, we are checking message authentication code. But imagine if there is a scenario wherein which the two communicating parties, Alice and Bob, or the sender and receiver, they don't have trust on each other. So how do I ensure that, or how there is any kind of a dispute that is arising between sender and receiver? How do I resolve about the messages that are sent? So for that purpose, we have digital signatures. So these digital signatures are mainly meant in the scenario where we don't have trust between sender and receiver. So the main purpose of digital signature is to ensure that we verify the author, we verify date and time of the message that is sent in the form of the signature, and also we must authenticate the contents at the time of signing of the message. And finally, whatever the signature we create, it must be verifiable by the third parties. In case if there is any dispute between the sender and receiver, so any other third party should be able to verify the signature that is produced. So the digital signature function includes authentication, but if we ask whether the message authentication provides the digital signature, certainly not. So any digital signature function provides authentication as well. These are the differences between the conventional signatures. Typically, when we do it on a document, so it's conventional signature that what we do on the document is an integral part of the document. But when it comes to the digital signatures, these digital signatures, we send it as a separate. So that means the message and the signature of the message both goes separately. Similarly, a conventional signature, when the receiver receives a document, the receiver compares the signed signature on the document with the signature that already they have. So then only they verify that, yes, if both signatures are same, they say that, yes, it is authenticated. But for a digital signature, the recipient or the receiver do not have such type of backup signature. So the receiver needs to apply a verification technique, which is a combination of message and the signature to verify the authenticity. So that means if imagine that I'm signing, I'm making my signature like this, you verify that, whether this is my signature or not. This is the case of physical. But the point that doesn't hold, this point doesn't hold in the digital signature environment. Similarly, in the conventional signature, you have one-to-many relationship between the signature and document. So that means if this is my signature, this holds for any document that I sign. But for a digital signature, there is only one-to-one relation. So that means when I take a message, the signature that digital signature that we get is unique to that particular document or the message and does not hold that for the other documents. So we have to create for other documents. In a conventional signature, a copy of the signed document can be distinct from the original one. In a digital signature, there is no such distinction. So these are all we are discussing so that we understand the digital signature aspects, because in the upcoming slides, we are going to talk about in the post-quantum cryptography environment, we are going to talk about these signatures. So if we take a message, what typically we do is first we create hash of the message. Subsequently, that hash of the message would be signed with the help of private key of the sender. So we use private key of sender for signing the document. So that forms the digital signature. So there are several algorithms to create this private key based digital signatures or digital signature generation algorithms. So once this digital signature is created, this would be appended to the message. So if you look at, so for this particular message, the signature has come based on hash of this particular message. That means this is unique to this particular message alone. So I have taken the message, created a hash. The hash is signed with the help of sender's private key. Now the receiver receives it. So the receiver receives the message and the signature. Take the message, what the receiver is going to do to verify the document, take the message or the document, calculate the same hash over that particular message. So get the hash. Subsequently, take the signature. The signature would be verified with the verification algorithm. And what is the input to the verification algorithm is sender's public key. So signature is created with the help of private key of the sender. Signature is verified with the help of public key of the sender at the receiver side. So the input to the verification algorithm is the hash of the message. Similarly, the second one is the sender's public key. Both are given as an input to the verification algorithm. If the verification algorithm is providing as a valid signature or not to the message. If the message is valid, then we get a valid signature, or else if the signature is valid, we take the message, otherwise we discard the message, or we say that the message got compromised, the signature is not verified. So this is the digital signature scenario. So the purpose of digital signature is to provide message authentication, integrity, non-repudiation, and on top of that, if we want to ensure confidentiality, we need to do the encryption of the signed document and the signature. So in that way, we can even ensure the confidentiality. So if you have the confidentiality, this is how it goes. So we have RSA-based digital signature schemes. We have Elgamal-based digital signature schemes. Then we have the digital signature algorithms. We have elliptic curve signature schemes. So now if we look at all these schemes are public key based. Public key based in the sense the signature is created with the help of private key of sender. Then verification is happened with the help of public key of sender. Right. So that means these schemes are all public key based. Why we discussed all this is that number one, we know that the public key based schemes are all prone to the attacks from quantum computer in the days to come. So the current digital signature standards would be at risk when once the quantum computers are materialized, right? So what are the algorithms that we have? This is the RSA based approach. This is the DSA based digital signature algorithm for creating the digital signatures. So I'll just touch the what is RSA based approach. So you take the message, calculate the hash of it, create the signature with the help of private key of sender, then send the message and the signature to the receiver. Receiver receives the message, then perform the hash over that particular message, then subsequently perform the decryption of the message with the help of public key of the sender. So this is how the signature verification happens, and then compare both. Then there is another standard algorithm called digital signature algorithm for creation of the digital signature. I'm not going to touch about this. So these algorithms, if we look at especially the public key based algorithms, they're all rooted to some of the mathematical problems such as prime factorization or the discrete logarithm problems. So these were chosen because it is computationally easy to combine large numbers together. However, it is computationally difficult to factor them or calculate the discrete logarithms. So currently, there are no mathematical algorithms or shortcuts to these algorithms. So that means, we are our algorithms are providing security. But when in contrast, these problems, if quantum computers have come, they are actually going to be broken with the help of some of the algorithms. So far we discussed the various cryptographic primitives in terms of symmetric, asymmetric, hash functions, message authentication codes. We also discussed about the digital signatures. Now let us discuss briefly about some of the quantum computing principles. The classical computers or conventional devices are the current generation computers. We are able to make them more and more faster by by making these operations of these computers faster, either by increasing the clock frequency or increasing the number of operations completed during each of these each clock cycle of these systems. But in 1993, the Bernstein et al. Have showed that the quantum computers violate the Turing thesis, and in 1994, Peter Shor has showed a practical example of the quantum algorithm, which is called the Shor algorithm. But the point is that at that time, we don't have the basic building blocks of quantum computer, which is called a qubit. So what are the quantum computers? I'll just go quickly to the quantum computing principles. If you look at the quantum computers, these as per the wave particle duality, these quantum computers are built, wherein which whenever we look at any object, it looks like a particle, but when we don't look, or else when we don't observe, those particles behave like a wave. This is called wave particle duality, based on which quantum computers are based upon. If you look at what is the fundamental blocks of quantum computer, the way the information is represented, we all know that conventional systems, they use bits, which we are going to represent the information in the form of either zeros or ones. Whereas in the quantum computer, these bits, we call them as qubits, wherein which these bits are basically read either both in the form of 0 and 1. In the sense, this is the classical computer, wherein which we have 0 or 1, which is the discrete number of possible states, 0 or 1. Similarly, they are deterministic in nature. In the case of quantum, we have infinite possible states for a quantum bit to be there, and hence they are probabilistic in nature. Further, there are other principles such as superposition, entanglement of these quantum properties that makes these quantum computers more and more faster and perform certain tasks which conventional computers are not able to solve. How this information is processed? In a classical computer, the bits process this information in a sequential manner, wherein which in quantum computers, the qubits work together in parallel to find optimal solutions of the problems, wherein which classical computers or classical techniques are unable to solve. How do we interpret the results? In classical computing, we have defined states or defined results are available, whereas in the quantum computing, answers are probabilistic in nature. And hence, typically what we do is we conduct the experiment couple of times, multiple number of times, to derive what is the answers for the problems that we have. So problems are run multiple times, and then finally we take the answers. So imagine if we have a system of 2 bits. Classically, the 2 bits can exist in 4 possible configurations, either 0, 0, 0, 1, 1, 0, and 1, 1. On the other hand, if we use a quantum computer, we can notice that all four possibilities could be encoded into a state of 2 qubits with the help of superposition. And we can see that all 4 possible combinations are available at a time for computation purpose. That's where the inherent parallelism is coming in a quantum computer. So these are all the various benefits. Number 1, superposed states, being probabilistic in nature, and having entanglement. That means bits or qubits can be joined together. And another important thing is wave particle duality. These are all the various principles on which quantum computers are built. So this particular slide shows, or the table shows, in comparison between the classical computers and quantum computing, and wherein which the quantum computers are providing various advantages over the conventional computers, especially in solving certain problems. When I say certain problems, problems where the classical computers are not able to solve. And because of that, what is happening? I'm not going to deal with the quantum computing principles or quantum computing building blocks, They are widely available. So I'll just go to the impact of this quantum computing on the various cryptographic algorithms. So if you look at this table, you can notice that there are symmetric encryption algorithms, there are asymmetric encryption or public key schemes. If you look at the symmetric key schemes, which AES is there, the encryption, what is symmetric encryption? In the case of quantum computers are realized, what we need to do is we need to increase the size of these symmetric encryption algorithms. They are not much affected by the quantum computers. Whereas if you look at all the public key schemes, they are no longer secure. Whether it is RSA scheme, whether it is elliptic curve scheme, or whether it is a digital signature algorithms, all these algorithms are no longer secure because of the quantum computers. So where or why this particular phenomenon is coming? So especially the most popular algorithm in the quantum literature is the Shor algorithm. The Shor algorithm is one of the main prime example in which the quantum computing phenomenon or quantum power is surpassing the classical machines, and hence we are solving some of the important problems such as the factorization problem. So what actually Shor did was, Shor actually had brought this particular algorithm or the problem into a problem called a period finding algorithm. So by converting the whole problem into a period finding algorithm, Shor has built a beautiful algorithm wherein which quantum computer is able to solve this particular problem. So let us see what happens with the case of Shor algorithm. Imagine we have a large number called n, wherein which we need to find the factors of this particular n. How the Shor algorithm is going to do is, these are all the various steps. So step 1, imagine there is a n to be factored, which is a large number and it has to be factored. For that purpose, what we do is that we are going to take a random integer, choose a random integer called k, wherein which the k is less than n. Then at step 3, we are going to calculate the GCD of the number to be factored and the chosen value k. Of course, we have Euclid's algorithm for that to calculate the GCD. If this GCD of k comma n is not equal to 1, then k is the factor. In case if GCD of k comma n is equal to 1, then we go to next step. We go to the next step. So in step 4 is the important step, wherein which we take a function. The function f of x is equal to k power x mod n for different values of x. So x is equal to 1, 2, and so on. So what we are going to do is we are going to calculate a r. We'll see what is that r. So at 4.1 step, we take a value called q, a variable called q, and assign it to 1. Then in 4.2, what we are to step 4.1, step 4.2, what we are going to do is we calculate q into k mod n, then check remainder of this. If remainder is equal to 1, then we go to step 4.3. Otherwise, what we do is we recalculate the q by q is equal to q into k mod n. Okay. So we reassign the Q value and to its remainder. Then repeat 4.2. The point is, we are going to count the number of such repetitions. This is important. So we are going to count number of such repetitions of recalculating the Q. So step 4.3 is, if step 4.3 is, we call R is number of iterations, that what we did in 4.2. This is called R. So then we go to step 5. What we do is, if R is odd value, then go to step 2 and choose a different K. If suppose if R is even, what we do is we choose remainder value in R power R by 2 round. So that means, imagine we have say 6 rounds of recalculating Q here. What we are going to do is, we are going to check R by 2th round. That means 6 by 2, that is the 3rd round. What is the remainder value? And we call that as P. Okay. So if P plus 1 is equal to N, then we go to step 2 and choose a different K. Otherwise, we go to step 7. What step 7 says is this: the factors of N are F1 is equal to GCD of P plus 1 comma N, and F2 is equal to GCD of P minus 1 comma N. So the algorithm at step 7 is able to calculate the factors of N, F1 and F2. If we go back to the algorithm, so what we did was, we took the number that is to be factored, then we have chosen a K value, we checked the GCD of the value to be factored and the chosen value using the K Euclid's algorithm. If it is, the GCD value is not 1, then what we did was, the K is the factor. Otherwise, we are trying to find or optimize a function called f of x is equal to K power x mod N. And while doing it, what we did was, we took a Q value, Q is equal to 1, and then calculate Q into K mod N, and we checked the remainder value. If remainder value is 1, we go to the next step. Otherwise, we recalculate the Q value. This recalculation of Q value is, we are verifying how many such recalculations are we are making it. That means the number of repetitions that we are making for recalculation. So if with that R value, if R value is odd, then we go to step 2. Otherwise, and choose a different K value. If R value is even, what we did was, we took the remainder in this R by 2th round and we call that as P. Then if P plus 1 is equal to N, then we went again back to the step 2 and we choose a different K value. Otherwise, we are going to the step 7, where in which calculation of these factors. So this is called Shor algorithm. The algorithm actually is able to do this particular whole process. If we notice, this particular calculation, especially step 4, is going into the quantum computer. The reason is this: the whole exploration of different x values at multiple x values is being done with the help of superposition of the bits, and hence things are happening at a very a faster scale through the superposition of the qubits. Whereas a conventional computers are not able to solve this particular function with a classical bits. So the core Shor algorithm, the core of the Shor algorithm is to transform the whole problem into the period finding problem. What is the period is that R is the period. So by transforming this whole process into period finding algorithm, Shor algorithm is able to solve the finding the prime factors of the number of a given number n. So this is the Shor's quantum factor algorithm that is available in the various literature, wherein which how this whole process goes. So if you notice, this is the period finding that happens in the quantum computer, whereas all the rest of the other steps that happens in the classical computer. So once the period is found, we are able to calculate the factors of the number. So because of this particular algorithm, if we notice, the Shor algorithm is providing a significant speed up over the other algorithm that is called number field sieve algorithm to address this particular problem, which is conventional computers are not able to implement it. But the practical implementation of Shor algorithm will actually make asymmetric encryption useless. So that means our Shor algorithm is able to address the prime factorization problem. So another algorithm from the quantum computers is the Grover algorithm, wherein which Grover algorithm main functionality is to speed up the unstructured search issues. Especially if we notice, one of the typical example is, imagine we are trying to find a phone number in an unsorted telephone directory. Typically, we need to use n number of steps. Imagine if there are n number of entries in the telephone directory. Typically, we may have to search n number of entries, or at least on an average of n by 2. But the Grover algorithm, it is going to speed up this particular finding the solution in terms of root n number of steps, which is a significant speed up. And because of that, the Grover algorithm, of course, I'm not going to touch what is the Grover algorithm, but because of the Grover algorithm, the typical cryptanalysis or brute force to find the symmetric key is becoming a major challenge, or becoming easy, especially performing the cryptanalysis. So if you look at to perform an exhaustive search over a key of 128-bit, typically a Grover algorithm would end up in performing 2 power 64 operations on a quantum computer, whereas we need about 2 power 127 operations on a classical computer. So this means the Grover algorithm is able to perform a cryptanalysis over the symmetric encryption algorithm. But what typically we can do is we can perform increasing the key size of symmetric encryption algorithms from 128 to 256-bit, or 256-bit of hash algorithms to 512-bit hash algorithms. So by performing increasing the number of bits in the key, we can at least save our symmetric encryption algorithms. But when it comes to asymmetric algorithms, they have potential risk from the quantum computer, especially from the Shor algorithm. So we discussed so far the cryptographic primitives. We just briefly touched about the quantum computing principles. Then we also noticed the quantum algorithms. Number one, the Shor algorithm. Another one is the Grover algorithm. Now, having said that, how to move forward, especially in handling the cyber security aspects or the security aspects of the current generation or maybe the future generation. If you look at, people are trying to implement the post-quantum cryptography algorithms. Then subsequently, there are algorithms that are coming from quantum computing principles, such as quantum random number generation, quantum key distribution. Subsequently, down the line, it is expected that if another 10 to 15 years of timeline, by the time the Shor algorithm and quantum computing modeling simulations and all comes, we are moving towards building the security solutions in terms of post-quantum cryptography solutions from the current trend which is happening, and then in the future we may have true quantum random number generations and quantum key distributions. So let us focus on what is PQC and as well as what is QKD of the quantum computing. So post-quantum cryptography algorithms, they are basically focused on building the algorithms that are resistant to quantum algorithms such as Shor algorithm especially. So we are having a set of algorithms under the umbrella of post-quantum cryptography, which are mainly aiming at addressing the issue that is coming from the Shor algorithm. Then QRNG means we are utilizing the quantum technology or the quantum computing principles, or we are harnessing the laws of quantum physics to produce truly random numbers. Now, all of us know that the current generation or all the cryptography algorithms, they typically use pseudo-random numbers or pseudo-random number generations. That means they are not true random numbers. But using quantum principles, we can build the quantum random number generating algorithms which are providing true random numbers. So that is QRNG. Similarly, we can use QKD, wherein which quantum computing principles and quantum physics are used to exchange the cryptographic keys. At present, as I've already mentioned, we are using asymmetric key principles to exchange the cryptographic keys. But we all know that so far as per our discussion, the quantum computing is going to make an impact over the public key or asymmetric key schemes, and hence they cannot be used for exchange of the symmetric keys. So quantum key distribution principles, algorithms are going to be helpful in exchanging and establishing the symmetric keys. So if we look at the post-quantum cryptography, the post-quantum cryptography algorithms are basically divided into various 4 categories. One is the hash-based signatures, multivariate cryptography, code-based cryptography, and lattice-based cryptography. So hash-based signature schemes are typically one-time signature schemes. They are used, and they are at a given point of time, they will be used for signing the given messages. So they are again based upon the hashing principles, which we have briefly touched upon in the very beginning. I'm not going to touch about the multivariate cryptography or code-based cryptography and lattice-based cryptography now, but I'll be talking about hash-based signature schemes. So cryptographic primitives based on the hash functions are called hash-based cryptography schemes, and they are used under the umbrella of post-quantum cryptography. And especially they are limited to digital signature schemes. We have seen what is meant by digital signature, wherein which given a message and hash of the message is calculated, and subsequently this is got signed. That's what we discussed while talking about digital signature schemes, while introducing the digital signature schemes. So NIST has introduced the stateful hash-based cryptography schemes under the name called Leighton-Michaeli signature or extended Merkle signature scheme. We will discuss about this Merkle signature scheme now. Here, when we look at stateful, means a state in the context of hashing schemes refers to recorded information. That means we keep some information about the hashing recorded, unlike in the stateless, wherein which we don't record certain information. We will discuss what is this getting recorded in the upcoming slides. So a hash-based signature scheme, which is mainly meant for hash-based cryptography. So first scheme goes like this. What we do is we pick 2 random strings, and then subsequently hash each of them and publish their output. Then what we do is we reveal the first pre-image to sign the 0 bits, the second pre-image to sign 1 bits. This is called Lamport scheme, and it is also called one-time signature scheme. Remember, the point is once the secret is revealed, it cannot be used for second time, and hence it is called one-time signature scheme. So let us see what is this scheme about. So I have taken 2 random strings. If you notice here, there are 2 random strings. So the string sk0, sk1, so wherein which each string has 256 bit length. So if you notice sk10, sk20, and so on, 256. Similarly, sk12, sk256. Subsequently, I am creating a hash of these strings and remember calling them as public keys. So this is secret key. I am calling, and I am calling it as public key. So I am going to use the pair sk0, sk1 as secret and pk0 and pk1 as public, wherein which my public keys are nothing but hashes of my secret keys. So what I do, I take the message and I see the string of the message. If my message contains a 0 bit, what I'm going to do is I'm going to use the secret key string 0 bit. So sk0, and imagine my sk0 has 1 to 8 as shown in this image. Similarly, my secret key 1 bits are given 1 to 8. So if you see 0 bit of the message, I'm going to use my the first bit of 0 secret key. Similarly, my second bit in the message is 1, and hence what I do is I take the second bit of my first or the sk1 string. Third bit of my message is 1. So what I do is I take third bit of my secret key string in the second key. Similarly, my 0 bit, my fourth bit of the message is 0. So what I do, I take from fourth bit of sk0 and I take it as a signature. So this is how I create the signature of the message I have. So I have 2 strings from the secret keys that I'm creating public key with the help of hashing those secret keys and keeping those pairs as a public key. Then what I do is how I verify it. Once I take the message and then I take the signatures. This is happening at the sender side and this is happening at the receiver side. So receiver, remember receiver knows pk0 and pk1. So message and the signature are received by the receiver. Receiver takes the message and corresponding signature, he hashes it. So hash value is compared with the public key hashes that are there. If both these hash strings are same, then it is concluded that the received message, the receiver signature is valid. So look at the second bit. The second bit is signature is 2, and the hash of this would be compared with the hash value of my second public key string. Similarly, third bit, hash of it would be compared with third bit of my public key string, second public key string. So this is how my verification happens. Remember, as I've mentioned, this is a one-time signature scheme. The secret key that is used cannot be repeated for other set of messages. So this becomes a problem to implement this particular hash-based signature scheme, which was proposed by Lamport in late 1970s. Subsequently, there are schemes called Merkle signature scheme. What happens this in the Merkle signature scheme is we are going to use the Merkle tree as the purpose of signing the documents or signing the messages. Root of the tree is regarded as the public key and which is the verification key. What is a Merkle tree? If you look at this particular tree structure, it is a Merkle tree, wherein which we can see here we have data items, data 1, data 2, data 3, data 4, and hash of these values we have at the leaves. So data 1 hash is hash 1, data 2 hash is hash 2, data 3 hash is hash 3, and data 4 hash is hash 4. And now hash of these 3 and 4 is hash 3, 4. Similarly, hash of 1 and 2 is hash 1, 2. And then hash of 3, 4, hash of 1, 2 forms my hash 1, 2, 3, 4. This is my root node. This is called Merkle root. This is how my Merkle tree looks. And this is the fundamental for the current generation, the current day blockchains as well. Look at the example of this Merkle tree. I have data elements called France, Germany, Denmark, Sweden, and all that. The data elements, hashes of these values, France, etc., and subsequent hash of these values, then hash of these two values, hash of these two values. If you notice, the Italy is only one element, so we have the hash of this goes as hash of here. Okay, so this is the example of the Merkle tree. When once we have the Merkle tree, we can easily check whether a value is included in the root hash or not. Imagine we wanted to test whether node 2, which is called Germany, is there in the tree or not. What we need is we need the node 1 hash. Similarly, we need node 3, 4 hash. So what we can do is we have the hash of the Germany, and we are checking whether it is there or not. So what we do is that we have node 1 hash value to calculate 1, 2, and subsequently we have node 3 hash value to calculate node 1, 2, 3, 4. And on the other side, we need the hash of node 5, 6, 7 to calculate the overall hash. So in this way, we can verify whether this particular element called Germany is present in the tree or not. So this is the way we can verify whether element is present in the tree or not, which is forming the basis for verification purpose. So how do we use this particular tree principle in the hash-based cryptography or hash C verification? What we do is we use the private keys to create the signatures. So if you notice, key 1, key 2, key 3, key 4, this is all private. We keep them private. The hash values and the final root, Merkle root value, forms the public key. So what happens is the sender also sends the authentication path along with the public key values. Okay, so this forms, so take an example, you notice authentication path of K3 is hash 3, hash 3, 4, similarly hash 1, 2, 3, 4, which is the public key. So at the receiver end, what the receiver would do is they can take this path and rebuild the tree using the verification key and verify or perform the authentication of the data item. So this is the fundamental principle on which the Merkle hash-based cryptography is working. And what we need to do is that if we implement this Merkle key-based authentication, we have to generate a bank of key pairs, say 2 keys, 4 keys, 8 keys, 16 keys, etc., and then create the public key from the root of the Merkle tree that as I've mentioned. And the point is that we must remember what are the keys we have used previously, and we should not use them again. And we have to use only unused ones. So if you remember, a few minutes back, we talked about statefulness. So what is statefulness here in the case of hash-based cryptography is what are all the things we are remembering about the keys is the statefulness. So there are algorithms that are stateless algorithms, but the Merkle root-based hash cryptography is the popular one that is emerging as the post-quantum cryptography algorithm used for the purpose of authentication and signature purpose. If we notice, the classical signature algorithms that are based upon the public key schemes, they are actually are prone to vulnerabilities because of the Shor algorithm, whereas the hash-based cryptography schemes, we are secure against such attacks. So far we have talked about cryptographic primitives. We have talked about the quantum computing principles. We have talked about the Shor algorithm. We have talked about Grover algorithm, the impact of Shor algorithm and Grover algorithm, cryptographic principles. So in order to address those issues, we have post-quantum cryptography principles. Among them, we have talked about hash-based cryptography algorithms. Of course, we didn't deal with the other algorithms of lattice-based or code-based. Now, we are entering into the other dimension of the post-quantum cryptography, or using quantum computing principles to address some of the current challenges of cryptography. What is the main challenge of current cryptography algorithm is how to distribute the common key that is there between sender and receiver without leaking it to the attacker. So that is the common challenge of the key distribution problem. So we need a common key for the purpose of implementing secret encryption or symmetric encryption. In order to implement symmetric encryption, we need the common key. So how do we do that? So we have several schemes. As I've already mentioned, we have schemes from asymmetric encryption algorithms such as RSA and Diffie-Hellman, but they're all vulnerable. So how do we address this particular problem? Can we implement quantum computing principles of superposition, especially the entanglement? Under the umbrella of quantum key distribution, we have an algorithm called BB84 algorithm, which is exploiting the principles of quantum superposition, entanglement, and uncertainty to implement key distribution or key management. So once the key is distributed, algorithms such as AES, which are symmetric algorithms that can be used for implementing confidentiality or implementing the encryption. So what is quantum key distribution? It is a popular algorithm is called BB84 algorithm. Of course, there are several other algorithms, but we discuss here now BB84 algorithm, which was developed by Charles Bennett and Gilles Brassard in 1984. And it was the first cryptographic protocol that is implemented in order to implementing the quantum key distribution and ensuring that if there are eavesdroppers listening to this communication, that is getting detected. So how it is being done is, imagine Alice and Bob, who are the communicating parties, they wanted to share the quantum key. There are some information which they send it in the quantum channel. There are some information that she share it in the classical channel or the open channel or the public channel among themselves. So once they do this, the common key gets established. So what they share in the quantum channel is about they transmit the quantum states about their keys. And what they share in the public channel is that in order to create these quantum states, what are the bases that they have used, that they share it in the public channel. The point is that if anybody is listening to this communication, then the quantum states gets collapsed. So that's what is the beauty of this particular algorithm. But the point is, we need to have proper infrastructure, quantum infrastructure, to implement this particular set of algorithms. So at present, there are laboratory-based experiments that are getting happening in implementing this algorithm. But down the line of, as I've mentioned in the couple of slides back, we need quantum infrastructure for this particular case. So let us see what is this BB84 protocol, which is used for exchange of the keys. In this particular protocol, the information is encoded in the form of polarization of photons, wherein which polarization can be performed either in two bases called rectilinear basis or diagonal basis. So the sender side chooses one particular basis or one particular approach, either basis or approach, we call it in either of the names, basis, to use the bits that they want to transmit to the receiver. On the other side, what happens, the receiver would choose either his choice of basis, which may be similar to the sender basis or different from the sender basis. Now, what they share is that what is the information they have established with the help of this particular basis. If both agree to that information, they keep that bits that are transmitted, otherwise they discard the bits. So now let us take this example. So imagine this A and B, they are sharing this information. A is transmitting the bits in this particular manner, 1, 1, 0, 0, 0, 1, 1, 1. And for that particular purpose, the Alice or the sender using the basis, what I have mentioned is rectilinear basis or diagonal basis. So this is the angle that is used in the polarization of photon polarization, 90 degrees, 45 degrees, 0 degrees, 135 degrees, and so on. Whether the receiver uses the same basis or not, it is the choice of the receiver. So accordingly, the receiver will get the bits as per the basis that what the receiver has used. Now, receiver will inform this to their sender, what are the bits that receiver has got. If sender says that, yes, this is the bit I have sent, then the receiver would keep those bits, otherwise the receiver will discard. If you notice, the bit that was sent by the sender is 0, whereas what the bit that the receiver gets is different. So such type of bits are discarded by the receiver. After completion of transmission, the receiver will keep these bits as the key, and the sender also keep these bits as key. Now the point is that by chance, if anybody is listening to this particular communication channel, what happens is that it will result in quantum errors, or else all this communication gets collapsed as per the quantum computing principles. In the sense that we are able to identify if there is any kind of a eavesdropper. So BB84 protocol is the one with which we are able to exchange the keys. So this forms the symmetric key. And once this symmetric key is established, communication can happen with any of these symmetric encryption algorithms. So with this, we actually covered all this gamut of topics. Number one, we talked about the symmetric, asymmetric, hash functions and digital signatures, which are the cryptographic primitives. We also briefly touched about quantum computing principles in terms of what is a qubit, what is a qubit, what is a superposition. Of course, I have not dealt in detail about these principles. These are widely there. Talked about Shor algorithm and also have talked about Grover algorithm. In terms of post-quantum cryptography, we talked about hash-based signatures or hash-based cryptography. Then quantum key distribution called BB84 protocol, wherein which that is used for establishment of key for symmetric encryption purpose. The point is the QKD, in order to implement it, we need proper infrastructure of establishing quantum channels, and which is going to take some more time in order to implement the potential application of this algorithm. But again, the literature also is showing about certain attacks on these protocols. So what is the roadmap ahead is that all the enterprises or the stakeholders in the whole digital environment, they need to verify their cryptography strengths of the algorithms. In case of symmetric encryption, they need to either increase their key size. In case of asymmetric, they need to migrate toward quantum resistant algorithms from the post-quantum cryptography. And in the longer term, if quantum computing hardware gets materialized, we need to go for proper standard algorithms of cryptography. So these are all the various books which I have, or books or the articles that I have used. Post-quantum cryptography from the Nature journal. So especially this particular book, Encryption for Organizations and Individuals, the basics of contemporary and quantum cryptography, is one book which has provided a wide variety of cryptography attacks, principles, techniques, and quantum computing principles, and also the various quantum computing algorithms. And also there is a book called Introduction to Post-Quantum Cryptography, which is another interesting resource. And there are various algorithms that are coming from NIST, and it is providing standardizations of the post-quantum cryptography algorithms. There are various challenges, and the NIST is coming out, and hopefully that we are going to have certain standards as well. So with this, I would like to conclude my talk of the quantum computing and security. Any doubts, I will be happy to, or any questions, I'll be able to take.
Yeah, I have a question. For the quantum resistant algorithms, those are implemented using conventional classical computing or implemented using quantum computing?
I'm sorry, can you please repeat the question?
The quantum resistant or post-quantum cryptography algorithms, those are executed using classical computers or can only be executed or implemented using quantum computers?
Yeah, so when we look at the post-quantum cryptography algorithms, whether it is hash-based algorithms or the whether the the code-based cryptography, lattice-based cryptography algorithms, these are all actually said to be resistant to the attacks from the algorithms such as Shor algorithm or the Grover algorithm. So, and hence, they are providing security from the quantum principles.
But they are executed using classical computers?
Correct. Yes, yes, at present they are. Yes, yes.
Got it. So these are algorithms to protect against attacks from quantum computers.
Correct. So if you notice even the Shor algorithm, there are certain steps that are executed at the quantum computer, especially the period finding, the calculation of R, what I have mentioned, is the one which is being implemented over the quantum. But if you notice, the rest of all the other steps, they are all implemented or executed over the classical computer.
And by doing that, an attack from the quantum computers will not happen.
In this particular algorithm, the Shor algorithm, attack from quantum computer means to find that particular period value which is R. So if you notice the algorithm, what I have narrated here, we are actually trying to find this particular value called R, which is total number of iterations we have done in this step 4.2. So this is being implemented in the quantum computer. If it is done, then we are able to address or calculate what are all the various factors. So this is the potential threat. And rest of all other steps are from the classical computer.
And those can be broken using classical algorithms if possible.
Yeah, classical, when I say classical algorithm, the whole steps, if you look at this part goes to the quantum, and the output of quantum comes as an input to the classical again, and then we are able to find the answers. Once we know the answers, the factors, breaking the key is easy, and it is done by the classical.
Got it. Thank you.
Okay, any other questions? Yeah.
And you also mentioned there is a random number generator, quantum random generator, which is more robust than the random number generators that are executed or implemented using classical computers, right?
So if we see here the random numbers, we have in various cryptography algorithms, we have to generate the random numbers, and all these random numbers are generated at present using the pseudo random number generator algorithms. So that means either you depend on the system parameters such as clock or whatever it is, and hence they are all actually not a true random numbers. Whereas the true random numbers can be generated with the help of quantum computing principles. And again, there are proposed algorithms for this. So yeah, that means in one dimension is that we are worried about the quantum principles in breaking our asymmetric, and on the other side, we are using the quantum principles to make the true random numbers, which actually provide strength to the security.
Okay. So with again, it is implemented using quantum computing.
Correct. The principles are quantum computing. Yes, yes.
Thank you very much.
And similarly, the quantum key distribution is also a dimension wherein which we are harnessing the principles of quantum computer to exchange the keys.
So there's a question on the chat window, and it reads, what about continuous variable QKD approach in terms of security and noise? Does it have any advantages?
Yes. So the point is, the current the quantum computers, people are called, whatever the small number of qubits with which the systems that are quantum computers are built, they are all called NISQ, which is meant by a noisy intermediate state quantum computers. So we don't have actually the full-fledged quantum computers which are not prone to the noise. So noise is one factor which is actually making an impact of the quantum computing developments, where people are working to minimize such noise. So in that way, actually having noise will actually hamper the key distribution problem. So what the QKD we discussed is about, once we establish a noise-free environment or a noise-free quantum communication channels, if they are implemented, in principle QKD can be used for establishment of the keys. But with the current noisy environments, it is extremely difficult.
Okay. I don't see any other questions on YouTube or on Zoom chat. But I had I was curious about this Y2Q, right? There's a lot of momentum with respect to Y2Q in US at least. So is there similar momentum in India as well? I mean, is Y2Q a very big thing?
Number one, a couple of researchers at individually and also at various organizations, they're focusing on the quantum computing. I think the DST also, which is one of the prominent funding agency, they are also actually trying to come up with a funding scheme, and also the another premier organization, IIT Madras, is also working very rigorously on this the computing principles. So yeah.
Okay. I think it is already late for you. It's past 11 o'clock, I believe, in India. So
Yeah, that's right. Yes,
I'd like to thank you so much for this detailed talk on a very important topic. I just wanted to share my screen, and if it was in person, we could have presented a memento, but in the absence, I just wanted to present you with the certificate of appreciation from the chapter. So thanks a lot again for
thank you.
the excellent talk today. And I wanted to conclude with a slide on the next talk we have. It's from Don Colliver. He will, it's actually a session. He's a author of the best-selling book on transforming public speaking with clown presence. He will talk about how to deliver a compelling technical talk. It's not just a talk, actually. It's going to be a session with participation from the audience as well. And hopefully everyone will take advantage of this.
Certainly, that would be great. Sure,
Yeah.
sure. So maybe you can share this link via email. Maybe I'll also circulate among our colleagues and scholars.
Yeah, that will be great.
Yes,
I'll
yes,
do
sure,
that.
sure, definitely.
Yeah. So thanks everyone for joining, and hopefully we'll see you in the next meeting next month.
Definitely, definitely. Thank you, Dr. Vishnu.
Yeah, thank you, Dr. Aswani.